I am now going to start up the EDU and perform memory tests on this capacitor, demonstrating all of the different curves that we just saw from a theoretical point of view and from a measurement point of view in my presentation, but here this will be real time. Start the EDU, and you'll see the D6 start to blink on the EDU, meaning it's running. It's a very simple menu to run the EDU for a very simple tester. Configure the test, execute a test. These are plotting and data management buttons that will become active if there's data to manage. We can ignore these three controls. There are 4 steps that need to be taken to configure the test. First, I need to select a custom ASCII profile for the waveform that I want to execute. In this case, a 2 millisecond pulse, 2 millisecond read. We use 4.89 volts for Vmax. The reason for 4.89 is I want 4 volts at the top of R1. The EDU has 300 or 330 ohms of output resistance. The voltage drop across that from 4.89 volts will result in 4 volts at R1 when I'm using a 2200 ohm value for R1. None of these other controls matter, and you shouldn't change them. I go to the second page for plotting. I want to display the oscilloscope data because the oscilloscope channel in the EDU is capturing the output of the memory board, and I want to plot versus time. Not centered versus time, just polarization versus time. So let's review. Polarization versus time, display oscilloscope data, 4.89 volts. Those 3 remain constant the rest of the demonstration, but I might change to different files, custom files, to get the pulse width or waveform that I desire. I'm going to press down on the down button to make sure that the capacitor is, well, down. Execute a test. And here's my display. 3 panes: the output drive voltage, the oscilloscope channel, and the polarization channel. The polarization channel has nothing on it, so it's essentially 0. If I actually mark the data points, you can see that it's plus or minus a bit of noise. It's a very nice, quiet measurement system, but we're not measuring polarization, so we can ignore that. Here's my sensor output, and here's my drive voltage. Now notice on the drive voltage there's a little dip right here. This is caused by where the EDU measures the voltage across the output, and the effect of the output resistance versus the resistance of the R1 on the memory circuit. So you essentially see that it goes 4.5 volts immediately, then all the way up to 4.9 once the capacitor is saturated, and so we're reaching the voltage that we want to reach for this. Now let's examine the sensor output, the oscilloscope output, the output of the memory board in detail. First of all, I want to see it magnified, so I press the right button, see maximize. Now I have the entire plot. Notice it goes from 0 to 10 milliseconds. I can use the cursor by pressing the left button and drawing a box, expand out the plot. Here's my shelf voltage, low capacitance, saturation. I can hit the right button again and say mark the data points. Now the EDU has a maximum sampling rate of 50 microseconds. Looking at the x-axis, which is in milliseconds, you can see each gradation here is 50 microseconds. Let's hit the right button and say I want to do X and Y grid lines. Again, you can see here's 1, 2, 3, 4, 1, 2, 3, 4, 5 steps across 250 microseconds is 50 microseconds per point. The reason why the waveform is shaped the way it is with 0 and 0 is because the EDU requires a minimum of 5 milliseconds. In this case, I'm using 10 milliseconds with enough points. 5 milliseconds And so at a 50 microsecond period, right, that's 100 points. I'm using 200 points, which is 10 milliseconds at 50 microseconds per point. Using that basic framework, I can expand the width or decrease the width of the pulse simply by changing the list of voltages in my ASCII file. So 150 microsecond pulse width would be 1, 2, 3 steps of voltage. Now in this case, the voltage went all the way up to 4.89 volts and stayed there for just a little bit over 2 milliseconds. And this was the charging rate of the capacitor, the output of the circuit, because of the RC time constant. Now I can close this plot by pressing the escape button or clicking on the top banner. Press OK, and it's gone. Now we know the capacitor is up, so if we execute another 2 millisecond read to saturation, we should get a non-switching curve. Sure enough, there it is. Mark the data points. Notice the difference in the output voltage at each point. And this is our memory window, as they say in the IC memory business. Saturation out at this point. Here's my shelf voltage. Here's where the remnant polarization is switching, is in this region. Past here, there's very little remnant polarization switching. Here, there's just a little bit. So we're going to stay between these points right here for our memory. Next test, I'm going to switch to a 150 microsecond test. I can check which file it is, right here at 150 microseconds. The capacitor is still up, so I should follow the non-switching curve. Here's the red. Sure enough, that's exactly what it does. If I maximize, mark the data points, expand this out, here we go, 1, 2, 3 points, exactly following the non-switching curve. If I press the button to force the capacitor down again, now when I execute the pulse, I should follow the non-switching curve. And what's amazing is that it does it exactly. Let's go back and look at this. Mark the data points. Here we go. Switching and non-switching pulse. Now, one of the things to note is that if I put the grid lines in, I can actually go to the customization dialog, set the style, and set different colors for the different traces. So I have black for the non-switching short pulse, green for the non-switching, for the switching short pulse, red for the profile or the trajectory, and blue for the trajectory. And what this shows is that the capacitor, when it charges, follows a trajectory on its voltage. It always follows the same trajectory, but that trajectory is determined by the memory state of the remnant polarization, and that's what we're going to utilize for our analog memory. Now, I can turn around and apply a bunch more pulses and see how many it takes to saturate this. So I'm going to execute. Press the enter button to close the plot. 2, 3, 4, 5, 6, 7, 8, 9. Maximize. And here are my pulses. I put in my data points. Pulse 1, 2, 3, 4, 5, 6, 7 in this case, to saturate the capacitor at a 3 value for the grid line. So I could actually get 7 counts of this. 1, 2, 3, 4, 5, 6, 7. And then it saturates above that point. Now, What I next want to do is build the shelf voltage using the pulses in the manner that I described before. So I'm going to clear the data so my screen is clear. I'm going to configure for the 2 millisecond test. Put the capacitor down. Execute the test. Execute the test again. I now have my profile. I will configure the test for 0 delay, say OK and execute. We know the capacitor is up, so we're going to get this. I'm going to go down, execute again, and we reproduce the same plot we had before. Now what I'm going to do is select a 150 microsecond test with a 100 microsecond delay. So it just shifts the pulse down in time. So I should be partially up. If I execute my test, follow this path. Configure again for 200 microsecond read. This next one. Configure again for a 300 microsecond delay. Configure again for a 400 microsecond delay. And configure again for a 500 microsecond delay. Maximize it. Here's my shelf reproduced. Now notice that it doesn't, that once I pass the shelf, that I begin to fall off the track. And the reason for this is because the pulse width is sort of narrow and is taking time to get all the way up. In this case, we already used a 2 millisecond test to get the capacitor totally saturated up. Here is traversing a different path because the pulse width is starting to slow down how much of the remaining polarization can be switched in pulses. So it's a nonlinear device. You change how it's stimulated, and you get a different result. That's also affected by its memory state and its history. So for the final demonstration, we're going to clear the data. And run a standard memory test as described earlier in the presentation. So I'm going to go to my 150 microsecond with 0 delay. I cleared. I'm going to put the capacitor down, execute a test, close the plot with the enter key, execute the test, and you can see the pulses building their profile. Maximize, show my box. Here's my test. 1, 2, 3, 4, 5, 6, 7. Now in this case, if I look at the grid lines, I can choose 3.2 volts or 2.7 or so. So this is purple, green, and a turquoise. Purple, green, turquoise. So I'm going to use 2.9 as my reference voltage. Undo the zoom. 2.9 gives me 1, 2, 3, 4, 5, 6 pulses, which is generally the range in which this operates. Now that I've determined that, I'm going to clear the data, put the capacitor down, go put it into my pulse generator, whatever is sensing environment, execute it twice, and clear the data. So whatever our sensor was, it saw 2 pulses. Take the board out, put it back in the EDU, and execute the test. 1, 2, 3, 4, 5, 6, 7, 8. If I come back, maximize, and look at my count, grid lines, 2.9 volts. Right here, I have 1, 2, 3, 4 before I saturate. 2.9 volts. So there's 4. We know the count was 6. That means 2 were put in. So let me do this again. Down, and let's do our count, because the capacitors move around a little bit, and so you want to always determine the maximum right before you do your analog storage. 1, 2, 3, 4, 5, 6, 7, 8. Maximize. Grid lines. 1, 2, 3, 4, 5, 6. So really 2.8 is a better threshold for us. Okay. Put the capacitor down, take it and put it in your external circuit so it does a count. I'm going to clear the data, do a count of 1, 2, 3, 4. So our device was put in a circuit that sent 4 pulses its way. We clear the data, pull the board out, stick it into the EDU control board, and let's count how many we have left. 1, 2, 3, 4, 5, 6, 7, 8. Maximize. Measure our path, grid line, y-axis, 1, 2. If we look at this, 2.8 volts is right here. And so we had a count of 2. 1, 2, 3, 4, 5, 6. So we could also use 7 as a count if we wanted to. 3.1, 3.2 volts is our reference. We had a count of 2. We know the maximum count for 2.8 volt threshold was 6. So we had stored 4 pulses in the capacitor when it was out of the EDU circuit. This concludes the training video for using the EDU. I'm sure there will be questions. remaining as you learn to use this, but once you do, you'll gain a feel for how the capacitors work. They are living things in the sense that they interact with their history, so they can move around a little bit. You might find the count changing from 6 to 7 if the capacitors sit for a long time on the shelf. If you have any questions, contact Radiant Technologies. It's our telephone number in the United States, fax number, and the email address. Thank you.